Welcome back to A Slice of Physics. In the previous video, I introduced Lenz's law, which had a simple looking sentence, but that required a lot of deciphering to figure out. So in this video, let's take another example that uses Lenz's law. And in fact, it'll also use Faraday's law to get some more practice with that concept. We will take the example of a magnet that's spinning near a coil, and I will use that to explain how generators work in all of our power plants. All right, here's the problem we're looking to tackle. It's got a lot of information, so let's see what it says. It says a circular loop of wire with a radius of 10 centimeters and a resistance of 1.2 ohms is placed on a desk. Then a magnet is held above it with the south pole of the magnet facing the loop, which means the south pole is held closer to the desktop. And it tells us that in this position, the magnetic field in the loop from the magnet is 0.8 Tesla. Then the magnet is spun 1/4 turn over 5 milliseconds. That ms here is milliseconds. So it becomes parallel to the desktop with the south pole to the left. And it's asking for the induced current in the wire. And it wants the magnitude in amperes as well as the direction. So first, I'm going to take this kind of an orientation to set this problem up initially. So here's a loop sitting on the desktop. It's a circular loop, but we're seeing it in 3D, standing next to the desk. And here's the magnet that is being held above it. The south pole is closer to the loop. The north pole, let's say, is here. And the magnet has a third dimension as well. So that's the initial orientation. The final orientation is this magnet is spun, let's say in this clockwise direction. So same loop here, but now the magnet is spun. So its south pole is to the left and the north pole will be to the right. So let's label this. This is my initial condition, and this is my final condition. And since the question is asking for the magnitude and direction of the current, I got to use Faraday's law to figure out the induced EMF, and then use the resistance along with the EMF to get the current. That'll give me the magnitude. And then I got to use Lenz's law after that to figure out the direction of the current. So in this initial setup, with the magnet being held just above the loop, the magnetic field direction is going to be pointing that way through the loop. So let's call that B initial. And in the final setup, let me change colors to denote the final. The magnetic field lines will go like this. And so they are going parallel to the loop over here, which means if this loop was a ring trying to catch the magnetic field, it's going to catch none of it. So the B final goes this way, but the flux from it will be zero, as we will see. So just to work through the formality of this so you understand how all this works, let me show you the actual work to figure out the initial and the final flux. So we said that the area, the direction of the area is along a normal, a perpendicular line to the area. And in this case, the angle of the magnetic field, the external magnetic field to that perpendicular to the area is 0. So in this case, theta would be 0. So my phi initial was A effective times B, which was the same as A times B times cosine of theta. So in this case, the area of the loop will be, because it's a circle, it'll be pi r squared. The magnetic field will be whatever the question gave us, and it'll be cosine of 0 degrees. So putting the values in, this is pi times the radius was 0.1 meters because it was 10 centimeters. 10 centimeters is the same as 0.1 meters. Better to convert everything in SI units. I'm actually going to leave the units out of this, but we'll keep everything in SI units. The magnetic field was 0.8 Tesla and cosine of 0 is 1, so I don't need to write that here. And that, when you put it into your calculator, will give you 2.513. Let me keep a lot of decimals because these are intermediate numbers. I'll round only my final answer. Times 10 to the minus 2 Tesla meter squared. Or I could have written Weber. Now for the final, my area is still the same. That's my direction of area. And now the angle between the magnetic field and the area is 90 degrees. So in this case, theta will be 90 degrees. Let me write this as phi initial back on the previous work. And now I'm going to call this phi final. So that would be, again, A times B times cosine of 90 degrees now. And I don't even care what A and B are. Cosine of 90 is 0, so multiplying anything by 0 will be 0. So there are two things I want to note here. One is that the flux decreased. That'll be important when we want to use Lenz's law. And the second thing I want to do is figure out the induced EMF. So according to Faraday's law, the induced EMF was equal to delta phi over delta t, which then in this case gives me 0 minus 2.513 times 10 to the negative 2 over 5 milliseconds. So that'll be 5 times 10 to the minus 3 seconds. And since we only care about the absolute value, we will get a value here of 5.027 volts. Weber per second, or Tesla meter squared per second, is the same as volts. And finally, I can just use Ohm's law. Sorry, this is getting a little crowded, but I'm going to squeeze one more thing in here. Actually, let me not do that. Let me just go to the next slide. So I figured out that the epsilon induced, or the EMF induced, was 5.027 volts. And I also had that phi was decreasing between initial and final. So those were the two key takeaways from the previous work that I still need. And now I know the resistance. It was given to me in the question as 1.2 ohms. Let's confirm that. Go back over here. Yep, 1.2 ohms right here at the top. So epsilon induced is the same as delta V. So I can use Ohm's law to figure out the I induced would simply be epsilon induced divided by R. Delta V over R is current. So in this case, that'll be 5.027 volts over 1.2 ohms, which gives me 4.2 amps. The final answer I can round down to just 2 significant digits. So there is my answer. So we've solved half the question. We still need to do the direction. So in order to do the direction, I'm going to change my orientation. It's just easier to talk about this if I were to take a bird's eye view looking down at the table. So here's my loop sitting on the table. I'm now like a camera stuck on the ceiling looking down at the desk, or I'm standing over the desk looking down. And in my first situation, I had the magnet being held like this. The south pole was close to the loop and the north pole was close to the ceiling. In my final setup, the loop is still sitting on the table like it was, but now the magnet has been spun, so it sits like this: south to the left, north to the right. So this is what I would see standing over the desk. And what I care about is the direction of the magnetic fields. So the initial magnetic field would be dots, because the south pole is sitting on top of the desk. Magnetic field lines point toward the south pole. So the magnetic field line at the desktop will be pointing upward from the desk toward the south pole of the magnet. So this is my B initial of 0.8 Tesla. And the B final, I don't really care about, because the flux, the magnetic flux final value, was equal to 0. So that's what gave us the fact that the flux was decreasing. And according to Lenz's law, the induced magnetic current has a magnetic field that opposes the change in flux. And what that meant was, if the flux was decreasing, so if flux decreased, then B induced direction was the same as B external, or in this case, we said we will always take B initial for the external value. So putting all this together, we've got the loop sitting on the table, we're looking from above, and we know that the B induced direction is also going to be dots, because it'll be same direction as B initial, because the flux decreased. So in this case, this is the direction of B induced. So now, finally, I use my first right-hand rule. And so if I grab the top part of this wire, I make a thumbs up kind of gesture. And if I grab the top part of this wire, I have to have my thumb pointing to the left in order for the fingers to curl and come out of the screen at the bottom. As I move my thumb around this wire, when I get over here to the left, my thumb has to be pointing down in order for the fingers to curl out of the screen. And then the thumb here in this section will be pointing right. And then on the right hand segment, it'll be pointing up. So you can try that for yourself. As you move your right hand with the thumbs up gesture, you will see that that is the direction of induced current you need in order to produce the magnetic field induced pointing out of the page. So this gives me the direction of I induced. So that's basically all the answers that we needed for this question. We got the magnitude figured out. The magnitude on the second page was 4.2 amps, and we got the direction figured out. So we can say that the direction is counterclockwise when viewed from above the disk, like a bird's eye view. All right, this problem is solved, but let me just take this opportunity to tell you how every generator works. We all depend on generators to get power in our homes, and so let me tell you how it works. So let's take a horseshoe magnet here. I'm going to try to draw the 3D. It's much easier for me to draw this on a piece of paper than on the screen, but hopefully you will see what I'm trying to show you. So let's say this is a horseshoe magnet, okay? And let's say this is the North Pole and this is the South Pole. We know that the magnetic field lines point from north to south. So I have a region of space in which the magnetic field line is pointing this way. And in that region of space, I can put a current coil or a coil that'll start carrying a current. So let's say the coil is placed like so, and a piece of it comes out here, and there's like a big paddle connected to it over here. And what I do in every generator is I use some force of nature to spin this. So it could be a waterfall. So there could be a waterfall over here and the water is falling over. And as it does that, it's going to hit this and spin this guy. And as it spins this, the coil itself in the presence of that magnetic field is going to spin. And as that spins, we're going to have current generated in that coil, and then we can connect more wires to it to take that current away to the homes that we want to power. So every generator that we have, whether it's a thermal generator which uses coal, so in that case, if you're using coal, you end up boiling water and have steam go up a shaft at a high pressure to turn the turbine. If you have a waterfall, you can see how that'll turn it. And if you have a nuclear power plant, generally that also creates steam at a high pressure by using nuclear energy, which then spins this turbine. So in all cases, we find a way to spin a loop in the presence of a magnetic field to create a current. So you can think of a generator as converting mechanical energy. So the mechanical energy is the energy of the spin of the loop to electrical energy by spinning the loop in the presence of a magnetic field. So in this slice of physics, we took another example of Lenz's law to decipher that one simple statement and figure out how to use it in practical cases. We took the example of a spinning magnet near a coil, and then we used that to set up the explanation for how every generator in our world works. Thank you.